I'm still tossing.
Okay, we're recording. Let's see here. A quick double check. Yeah, okay, good. Okay, so last time we were talking about different ways to represent functions with pictures. Very importantly, you got to keep in mind that there is not just a single way to represent functions with pictures anymore, right? That was a Calc 1 thing where every picture is a graph, and so all of the interpretations that you make of calculus objects like derivatives and such. There was one geometric interpretation because there was only one picture being drawn. Not so any longer. So, for example, we talked about this one last time, so I'm not going to go through the details again, but this curve, this picture, right, this actually relates to several functions. And if you want to understand the geometry of this curve using calculus, well, you have to ask yourself, I'm taking the calculus of which picture, right? Am I looking at the graph? Am I looking at a function for which this is a level set, or a function that parameterizes this curve? Which of these functions should I be looking at because of, calculus of what am I going to be computing? So very important to always have a crisp and clear, unambiguous idea in your mind of which kind of picture are you looking at, and then interpret appropriately. Okay, so we talked about the details last time. Moving along, here's a neat fact. This is going to look like silly, trivial algebra, and it kind of is. You look at these two equations right here. Right? My gosh, nothing happened. I moved the stuff that was on the right over to the left. It's nothing happened. Really, they're literally equivalent equations, but furthermore closely equivalent, right? And yet, actually, something really important's happened here, and that is in how I can interpret these equations. So, in particular, I can think of the top equation as representing my thing as a graph. And again, here's how you recognize this as a graph. I know that I'm looking at this as a graph now because it says variable equals and then a function of the other variables. Right? That's what a graph is where you set the value of a function equal to a new variable. So this is a graph, and specifically this is a graph of this function here. Right? This function called little f, which has n input variables. Yeah, okay, fine, cool. But here's the thing. Having done this trivial little bit of algebra here, almost nothing happened. Notice this, I have something set equal to a constant. That's what level sets are. Right? So even though I didn't really do anything, this bottom equation allows me to interpret this, whatever this surface is, as being a level set, not a graph. And specifically, it is a level set of the thing that I'm setting equal to a constant, which of course is not the same function. I am not setting f equal to a constant. Absolutely not, right? I'm setting this other thing called y minus f, which you'll notice is no longer a function of just x1 through xn. This is not a function of just those n variables. This is also, this expression right here has a y in it. This expression that I have in light blue is also a function of y in addition to all the x's. So this is a function of n plus 1 variables. So different expression, different, function of a different number of variables, totally different function, right? That this is a level set of. So what's nice about this is that you can always do this for any graph. Anytime you are looking at a graph of a function, well, this is the equation of a graph. This little algebraic triviality is always doable, and therefore you are looking at a level set of a different function. So whenever you're looking at a graph, you can reinterpret it as a level set. And why do we care about this? Well, because again, the calculus of graphs and the calculus of level sets are different. And if the calculus of graphs doesn't tell you what you want, which by the way is regularly the case, right? Calculus of graphs isn't cutting it. Pull this little fast one here, right? And now we can talk about the calculus of level sets of this other function. It's a foot in the door to try something else. Let's see an example. So here is a function. Maybe I want to know something about the graph of that function. And of course, we form the graph of this function by setting the value, output value of the function equal to z. So again, why do we want to know something about this, the graph of this function? Whatever, some context it comes up naturally, let's say. And again, maybe the calculus of graphs, what I know how to do with derivatives of this function and interpreting that in the graph context might not tell me what I want. So I do this little trivial little algebraic, little sidestep here. Hardly anything happened. A little bit of trivial algebra. And now I get to say, oh, well, hey, look, check it out. I'm looking at a level set now. See, I've got equals constant. This now is a level set. Specifically, it's a level set of this function here. And so I can apply now the calculus of level sets, whatever that is. I know we haven't talked about that yet, but we will soon. The calculus of level sets that we will see soon is something I can apply to this function. Not that one. Very important. Not this one. Don't do the calculus of level sets to this function. That wouldn't make any sense at all. I'm not looking at a level set of that function. Calculus of level sets applied to this function will tell me different information that might be useful, might be something that the calculus of graphs of that function didn't tell me. Okay. Everybody on board? Yeah.
Yeah, just to make sure. So in this case, if x is like R2, then G would be R3.
The what now?
If f is R2 belongs to R2, G would like.
So
R3.
Those words don't fit together like that. So functions aren't in spaces.
Okay.
So a graph of a function is something that lives inside of a space, right? So f is a function of two variables. The domain is R2. Maybe that's what you meant.
Yeah.
The domain of f is R2. The graph of f is what we're actually interested in here. The graph of f is represented by this equation that has three variables, and so the graph of f lives in 3 dimensions.
Okay.
Yeah. Okay. All right. You'll see the value of this little slick move when we start getting into how the calculus of graphs and the calculus of level sets pretty soon, possibly today. Bad news, this doesn't go the other way. Every graph is a level set, but not every level set is a graph. An easy counterexample, here is a level set. Right, this is a level set of, well, apparently this function here. Right, so I'm looking at a level set, and by the way, I can draw what that level set looks like. That level set is this circle, easily recognized, right? Old high school algebra picture, and this isn't a graph. Fails the vertical line test, crash and burn. We're done. So wouldn't it be nice? I mean, algebraically, one way to look at this is that if I were going to turn this equation and if I were going to move things around, try to be clever and rewrite this as a graph, I would have to solve for either x or y, and I can't. Right? In the strict sense of the word. Now, a lot of people will tell you, yeah, I could solve for y, and I get 2 different values. If you want to talk about something as being a graph, you need a single value, because that single value has to be the value of this function you're claiming to look at a graph of. And so, in that sense, you can't solve for y because there are 2 possible values. Okay, so it fails the vertical line test, in other words. All right. Okay, let's talk about equations. How do we draw equations? Solution sets to equations of several variables. There are a couple of little tricks that are helpful, like the similar question in 2 dimensions. We're not going to be able to answer every such question, right? I mean, there are some equations of there's lots of equations of 2 variables that we don't know how to draw pictures of. It's hard, right? So likewise here, what we're going to do, though, is, again, tools for your toolbox. And this first one is a really nice trick that turns what seems to be a hard problem into an easy problem. And anyway, let's just dive in and do it. Suppose you have an equation of 3 variables. If, and that's a big if, this scenario that I'm about to describe does not come up all that often, but it's more than you would think, but it's not to be assumed. If, big if, your equation involves x's and y's only as part of this expression right here. If x and y show up in the equation only as part of square root of x squared plus y squared. No other x's, no other y's anywhere in the equation. So again, you see that's not every equation, right? There's plenty of equations that don't fit that rule. But the nice punchline, very powerful punchline, is that your surface is rotationally symmetric around the z-axis. And I love this little result because the condition you have to check is basically eyeball glance. Just look where the x's and y's are and see if they all fit in this form. And so easily checked, and once you've made that quick check, you instantly get a very powerful bit of geometric information about this surface you're trying to draw. Rotationally symmetric around the z-axis is huge information. All right, now why does this work? This is a pretty straightforward argument. If I have such an equation, and if I have a point that satisfies the equation, right? Let's ask, what would happen if I rotate that point around the z-axis? Now that produces, of course, a different point, a bunch of different points. But let's look at this one here, this different point. They're different points. They have different x's. They have different y's. But they do have the exact same value of r, a.k.a. square root of x squared plus y squared. Right? And they have the exact same value of z. And since this is the only thing that shows up in our equation, by assumption, the equation involves x's and y's only in this form. Even though the x and the y are different, they just compute the same value of this expression that all of those variables are wrapped up inside of. And so algebraic, I'll say arithmetically, these 2 points are going to go into the equation and do exactly the same thing. Either they both work or they both don't work. So that makes this surface rotationally symmetric. Now, if you don't like that argument, here's a different take. Totally different take. Let's see here. Let me clean up the mess. When you convert an equation from rectangular to cylindrical, if x and y only show up in this form, then that part of the equation is going to just turn into r. What else could there be in the equation? There can't be any other x's. There can't be any other y's. By assumption, all of the x and y's are this, which just turns into r. The only thing that's left is z, and z remains z. And so this equation, when you convert it to cylindrical coordinates, theta just doesn't ever have a chance to show up. There are no thetas in your equation. And if you have a cylindrical equation with no thetas, we talked about this earlier this week, I forget exactly when. No thetas in your cylindrical equation means, again, rotationally symmetric around the z-axis. All right, so now let's see. Why do we care about this? And now this next part is just a geometric appeal. If you have a surface that is rotationally symmetric around the z-axis, you can look at its cross-section in any plane containing that axis. Just take any cross-section and then rotate that cross-section around that axis. Here's an example. Let's see here. Let me get this all on the page. Yeah, okay. Let's look at this equation right here. Notice that x and y appear only in our special form. Now you may be complaining, hey, the special form had a square root. I don't see a square root here. Where's the square root? Okay, fair complaint. Let me point out, though, I can totally rewrite this as z equals square root of x squared plus y squared squared. Right? And so a little bit of a rewrite, but this is totally equivalent equation, and now, as required, x and y appear only in the special form. Is that cool? So it could be on the lookout for this kind of thing. You might have to do a little side step algebraically to make it fit, but that's totally fine. Okay, so now I'm going to look at a cross section. I'm going to look at the cross section in this plane right here, x equals 0. Notice the requirement. It does have to contain the z-axis. Let's see here, our axis of rotation here, the z-axis. And, of course, thankfully, x equals 0, the yz plane, does contain the z-axis. Okay, well, by the way, this does a tremendous amount for us algebraically. If I'm only going to be looking at the cross section in this one plane, that means I get to plug in x equals 0 into my equation, and that makes really good stuff happen. In particular, that makes this turn into, and I feel like my picture's getting a little muddled here, makes my picture turn into this. Just z equals y squared, and that is easy. That is an easy picture to draw. It's just a parabola, right? Algebra 1, or I don't know, algebra, high school algebra. Everybody with me? So because I'm looking in this one cross section, easy picture. And now, as previously noted, I know my surface is rotationally symmetric. I know what one of the cross sections looks like. That means I can literally just rotate that cross-section around, and that will generate my rotationally symmetric surface. And so, again, let's see here. So I'll do this in purple, I guess. So our original surface obtained by rotating that parabola around gives me this kind of a bowl, kind of a cereal bowl looking shape right here, which, by the way, just semantics, this is referred to as a paraboloid. You can probably see the motivation. Yeah.
How do you know that the cross-section is that x equals 0?
Oh, arbitrary choice. You can pick any cross-section you want. Now, it's got to contain the axis of rotation, but that is kind of the thing of beauty here. Is any cross-section you want. Now, again, geometric appeal. If I have a truly rotationally symmetric surface, those cross-sections all look the same anyway. So, yeah, whatever. Pick any one you want. I like this one because it's easy to draw, right? Pure laziness motivation, but, why not? Okay. Let me show you another example. Now, this next one here, different equation. What are we going to do with this? But notice, x and y appear only in the special form, and therefore this is rotationally symmetric around the z-axis. And I know I've said this several times, but I feel it necessary to say it again. It's not enough for them to appear in the special form. They have to appear only in the special form. No other x's, no other y's, just in the special form. Okay, so now pick your favorite plane containing the z-axis. This time, just to show off, just to show that I can do it, right? I'm going to pick the xz plane. Who cares? It doesn't matter. Pick any plane you like. Typically, I like the yz plane. Again, it's easier to look at. But anyway, here you go, picking the xz plane, aka y equals 0, which therefore makes my equation simplify very nicely. That y just goes away. That leaves me with this equation, which y'all will recognize as a hyperbola, specifically a hyperbola about like that. This is a cross-section of a rotationally symmetric surface. So if I just rotate it, now again, geometric appeal here, you have to visualize what happens when you rotate this hyperbola around the z-axis, and that result then is something that looks kind of like this. which is called a hyperboloid of one sheet. And we'll see in a moment something called a hyperboloid of two sheets. Yeah.
Could you rotate that about y equals x?
Could you what now?
Could you say like the whole plane where y equals x?
Yeah, you can take you can choose as your cross section plane. Yeah, you can choose the plane y equals x. The problem there is that it's for one thing it's at an angle. For another thing, the thing representing distance, like if you had that plane kind of like that, the thing representing distance in this direction is neither x nor y. And so in order to be able to make sense out of that, you'd have to rewrite the x's and y's all in terms of, let's say, r or something. And I'm going to call it make work, right? There's nothing to be gained from doing that. You could make it work, but it's unnecessarily confusing. Yeah, but totally fine. Okay, here's another one. This one, I'm going to adapt the argument. Correction, y'all are going to adapt the argument. Nice exercise. I want you all to think through. If you want to make sure that you understand the argument I've given you about rotations around the z-axis, I claim you can do the same kind of thing for the other axes. Think it through. If you get stuck, if you're not sure, come to office hours. Happy to talk about it. Nice practice, though. Good challenge to think about this on your own first. Okay, and with that said, let's think about this equation. Now, it doesn't leap off the page at you as there being, a variable squared plus another variable squared. But notice a little bit of algebraic finessing, right? And here it is. I've got y and z appearing only in the special form. Again, citing a theorem that y'all are going to think through on your own, because it's y and z that appear in the special form, that makes this, I claim, rotationally symmetric around the x-axis. Okay, cool. Rotationally symmetric around the x-axis. There's my x. Oh, come on, I can do better than that. There's my x-axis. And okay, well, if it's rotationally symmetric around the x-axis, I get to pick any plane that I want that contains the x-axis, my axis of rotation. Any plane that I want. I got a bunch of options. The xy plane is what I'm doing here, but I could have picked the xz plane just as well. Doesn't really matter. Suit yourself. That said, picking as I am the xy plane, otherwise known as z equals 0, and that turns my equation into this. And again, hyperbola. Again, high school algebra. And that's this hyperbola right there. So my cross-section looks like that. My axis of rotation is the x-axis. Now again, geometric appeal. You take this hyperbola and you rotate it around this axis, and you get a hard-to-draw thing. I've never really been happy with the quality of this picture that I'm trying to draw here, but I like to think of this as each one of these is kind of shaped like a contact lens, if you will, right? So I like to call this the staring contest, right? It's a bad sense of humor, but but nevertheless, it's still a rotation of a hyperbola, so we still call it a hyperboloid, but it's not one single thing like this was. Now it's two separate, what they call sheets, and so this is called a hyperboloid of two sheets. Everybody good? All right. Okay, so that's a tool for your toolbox. Look for opportunities to use rotational symmetry arguments. Really, really handy. Okay, next, what I'm calling deformations. So suppose you have an equation, and then suppose you tweak the equation. That's the premise that we're going to start with. So, for example, what if everywhere you see a z, you replace that with 2z in your equation? Oh, yeah, question.
A quick question about rotational symmetry. Is it like
shape only rotationally symmetric if it has that special form?
Yeah, that's the sticky wicket. Yeah, so the rotational symmetry argument only applies in a limited set of cases, and now again, it comes up surprisingly often, right? But only in those special cases does it apply. Yeah. Okay. Okay. So hypothetically, let's suppose we have some equation and we tweak it. Everywhere in my equation that I have a z, I replace it with two z's, such as, for example, let's take this equation right here, which, by the way, is an easy equation to understand. I have a couple of different points of view on how to think about this green equation. I could view this as rho squared equals 13 squared, and thus I have a sphere of radius 13. Spherical coordinates coming in handy, right? I could also make any of three different rotational symmetry arguments here, notice, right? I could argue that the x and y appear only in the special form, and blah, 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 right? So either way, pick your argument. This is a sphere of radius 13. Okay, so again, what happens, we ask, if everywhere in this equation that I see a z, I replace it with 2z. I have tweaked my equation. My new equation here, totally different equation. Absolutely not going to have the same surface. And easily observed. I mean, look at this. I mean, I can just literally take a point like 3, 4, 12 that works in the original equation, and it just straight up does not work in the new equation. Of course it doesn't work. Look at the 12. The 12 here was my z. The 12 was supposed to get squared in the arithmetic. That 12, when I try to plug it in here, the first thing that happens to the 12 is it gets multiplied by 2. Now it's 24 that's getting squared. A different arithmetic, crash and burn. Of course it didn't work. So the clever move then is to realize that if you, the problem was that 2 that we inserted. Let's kind of try to account for that, and let's put in this point where it's a 6 that goes in to where the z is, and that 6, when it gets multiplied by 2, becomes the 12 that we wanted to have squared, right? So it's the kind of hack way to make it fit under the new circumstances, if you will. Right? So, if you will, what's happened here in the process of replacing all my z's with 2 z's, my z coordinates get cut in half. And you can think of this then as basically vertically squishing your surface. Does that make sense? Okay. So this is a kind of a general rule. Whatever you do to a variable in an equation, the opposite happens to the surface. You replace z with 2z, the z coordinates get half as big. And likewise. Okay. So again, there's a bazillion different versions of this, and it's a good exercise to think these through on your own. But let me show you how you can benefit from this trick if you were to find yourself interested in this equation. Right? What's that an equation of? Yeah. It's not rotationally symmetric. Now, I see an x squared and I see a y squared, but they have different coefficients. And if I were to try to move things around so that x squared plus y squared is the only way that it appears, I'm going to lose. There's going to be leftover terms, right? Because the a and the b are not the same. So, not rotationally symmetric. You cannot make a rotational symmetry argument. I see an x squared, y squared, and a z squared. It's tempting to try to relate this to rho, spherical coordinates. But again, there's leftover terms. Rho, very specifically, is square root of specifically and exactly x squared plus y squared plus z squared. So these a's, b's, and c's are messing it up. So we don't have any tools for understanding that surface. What I can do, though, is say, it's not that different of an equation from this equation, which is easy. Right? Again, we have any of a number of different ways of understanding this equation. This is rho equals 1. It's a rotational symmetry argument about pick your favorite axis. Lots of options. Easy to understand that this is a sphere. So, when I realize that the only difference between these is that in the one that I understand, I'm replacing x with x over a, and I'm replacing y with y over b, and I'm replacing z with z over c. I'm just doing sort of 3 tweaks to the equation, and each one of these tweaks, each one of these replacements, I have an existing geometric interpretation of what they do. Whatever you do to the x, the opposite is going to happen to the surface. So by replacing x with x over a, I'm going to be stretching in the x direction by a factor of a. And stretching by a factor of a turns if you will, a radius of 1 in the x direction into a radius of a in the x direction. And likewise, b in the y direction and c in the z direction. And that's easy to understand, and it's easy to draw a picture of, because if I have a sphere and I start stretching it in different directions, I get something that's ellipse-like, and they call this an ellipsoid. Is that cool? Everybody happy with that? Okay. All right, couple more examples. I'm going to be really quick with these, time being a factor and all that. But we already know that this is a paraboloid, rotational symmetry argument, and that helps me understand what this is. This thing here. Well, I'm just doing a quick replacement of x and y. And so this is just going to be stretching my already understood paraboloid, stretching it in the x direction, stretching it in the y direction, thus making something that's just a stretched out paraboloid. We call it an elliptical paraboloid because those cross sections that were circles are now ellipses. Is that cool? Likewise, we've already studied this one. What's going on over here? Again, we're just stretching it out. Now, the one little algebraic landmine I want to show y'all so you don't step on it. How much, what is the replacement that actually happened here on x's? A lot of people would say, I divided by a squared. Not so. This equation I can rewrite as x over a squared plus y over b squared. So, in fact, everywhere I had an x, what it gets replaced with is x over a, not x over a squared. Right, so do be careful about that. You got to worry about the algebra, the devil's in the details, and this little detail devil does stings the occasional student. So do be careful. Likewise, y gets replaced with y over b and all that. Okay. So moving along. That finally finishes 2.1 for us. By the way, big section. Moving on to 2.3. Skipping 2.2. Right, you'll notice also 2.2 not on the content syllabus. You're not responsible for 2.2. I have mixed feelings about this. I guess it's always nice when I'm in a hurry, right, and not have to cover that. But it is unfortunate because 2.2 is about limits, and it's a big deal. If you really think about it, this is a multivariable calculus class. Everything that we're going to be defining in this class is going to be defined with a limit. Derivatives that we'll be defining over the next couple of weeks, really technically all defined by limits. Integrals, of course, also defined by limits. Multivariable limits there's actually a lot to say about it, and it's more subtle than a lot of people would think. So the mathematician in me is sad about the fact that we're not going to have that very important conversation about limits. But the reality is that as wonderful and important as that stuff is, it doesn't really affect the bottom line of solving problems, and that's just not what this course is about. So we skip 2.2. Anyway, I just wanted to point that out. Moving along to 2.3, we're going to talk about derivatives. There's, again, a lot to say. And very importantly, there's more than one. And in single variable calculus, again, not the case. In single variable calculus, there is the derivative. Multivariable calculus is more complicated. There's several, depending on how you count, arguably 4 or 5 different kinds of derivatives that all are distinct from each other in important ways. So how do we use the same word, derivative, to apply to a bunch of different things if they're all different? And that is that they have a unifying feature. We call these things that we're going to talk about all by the same word, derivatives, because they all have this common feature that they relate input changes to output changes. Right? And every interpretation you've ever had of derivatives in single variable calculus, there's different points of view you can take, of course, but the important unifying feature that all of those perspectives have is there a relationship of some sort between input changes and output changes. This is what's going to carry us forward with multivariable derivatives. Okay. Now, I'm going to start with something called partial derivatives for various reasons. It's easy, student-friendly, which is nice. It's relatable. It's going to be kind of familiar, also nice. And the book does it this way, and that just for logistical reasons makes it hard to do something different. And in past years, I have deviated from the book and gone off and done things in an importantly different order, and kind of like I did with cross products and determinants and stuff, except it's a much bigger deviation, and it's just not worth it, frankly. It's too bad. But that said, I want to emphasize, none of these reasons says that partial derivatives are fundamentally the right way to think about differentiation. And in fact, it's not. So this is an important idea, important warning. Eventually, you're going to have a completely different point of view on what a derivative is than what I'm about to show you right now. So think of this as a starter example that we're eventually, I'm not going to say we're going to abandon it, but we're going to demote this when we eventually, after doing some work, come up with a really much better, much more powerful, much more natural point of view on derivatives. So don't think of this as laying your cornerstone on differentiation. This is not the cornerstone. Okay. All right. Moving along. Here we go. Here's how you compute this thing called a partial derivative. You've got a function of several variables. You're just going to pretend that most of those variables aren't variables. You're going to momentarily say, let's treat them as constants. Let's suppose, hypothetically, let's pretend that these are constants, which is outrageous, right? They're not constants, they're variables. Yeah. But for the purposes of what we're going to consider here, we're going to treat them as variables. We're going to momentarily insist that they be constant. So already, I hope you're unimpressed. This seems outrageously unfair and unjustifiable to just pretend that a bunch of variables are no longer variables. Okay, and that's appropriate. So we're going to hold all the variables constant except for one. We're going to choose to leave a single one of my input variables still as a variable. And now if you think about it, I had a function of a bunch of variables, but now most of those bunch of variables aren't really variables anymore. Now I've got a function of, well, really just the one variable. And when you have a function of just one variable, that is a single variable function. And if you have a single variable function, you could just take the regular old, good old, plain old, regular derivative of that single variable function. So this is what a partial derivative is. And before I get to an example, let me talk about notation. Here is one of our primary notations. Notice it looks a lot like Leibniz notation for a regular derivative. The main difference being that we don't use a d. We use this little funny looking little kind of roughly D-shaped thing. So very important to recognize, this is not a D. You cannot use a D in its place. Not okay. That's highly inconsistent with standard notational practices, and you have to use accepted standard notations in this class. So you can't use a D. You have to use this little funny little kind of swirly D-like thing, but not a D. Likewise, a lot of people mistakenly think that this is a lowercase Greek letter delta, but it's not. The lowercase Greek letter delta kind of flops over to the right at the top. The partial symbol doesn't. So heads up about that. Please do be careful. You may or may not have ever drawn this symbol in your life. And again, as I commented before, when we were talking about Greek letters and spherical coordinates, you might need to actually go through the kind of humiliating process of teaching yourself how to write this character. I did when I was in y'all's position, and I filled up half a page and drew 75, 100 little partial symbols and kind of worked out the kinks of my own handwriting there. So anyway, for your consideration. Okay, so let's do one. This is a nice demonstration of what I said before about how easy it is to compute a partial derivative. Look at this scary looking function. Yikes. Right? Feels like this, oh my God, we're probably going to have to use like a product rule or something. And oh my gosh, look at this. There's a composition inside of which is a product. This looks like a nightmare to take a derivative of. Okay. Ugh. But, importantly, notice I'm taking a partial derivative with respect to y. That means y is the only one of these variables that I'm going to treat as a variable. The other variables I'm going to treat as constants. So x and z, that x is a constant. That means e to the x is a constant. This x here, constant. That z, constant. So this is constant. So that's constant. All of this is constant. So for the purposes of this partial derivative, which again, just a partial derivative, I haven't given you any reason yet to believe that this partial derivative I've defined is in any way useful, right? Other than I'm spending class time on it, and strategically you might speculate, right? But I haven't given you any mathematical reason to believe this is useful, and yet to compute it, by definition, I get to just treat all this stuff as constant. So I'm taking a derivative now of y squared times a constant. And the derivative with respect to y of y squared is just 2y. And the constants come along for the ride as, multiplicative constants do. Everybody happy? Super easy. Couldn't be better. Okay. Likewise, a couple of examples here. Now, again, here's a scary one. We have a function to the power of a function. Those are always creepy. Logarithmic differentiation, right? Bad memories, nightmares from high school calculus of logarithmic differentiation. But no problem. I'm taking a partial with respect to x. So x is my variable. What I have inside the parentheses there is my variable. Y, being as it is not x, is a constant. And so my whole exponent here, all constant. And so this is actually just a power rule question. This is not a function of the power of a function. This is a function of the power of a constant. And y'all remember how to do the power rule, right? The chain rule combined with the power rule anyway. Easy to do. I hope. By the way, don't forget, single variable calculus is a prereq for this class. It's in the prerequisite trail for this class. So I'm going to assume that you are glass smooth proficient with all of the old derivative rules, chain rule, product rule, quotient rule, derivatives of trig functions and logs and exponentials and all of that stuff. Right? So make sure you're fully dusted off and polished on all that. Likewise here, another scary looking one, but I'm taking the partial with respect to z. That means z is our variable. That means that all the other variables are constant. So x is a constant, y is a constant. That means this whole base here is a constant. So again, scary looking, but this is just constant to the power of z. It's an exponential. Simple exponential. And again, single variable calculus, we have long established rules on how to take derivatives of exponentials. So, nothing to it. Everybody happy? Okay, so easy to do. I nominate, by the way, partial derivatives as the most easy derivatives to compute, including single variable derivatives. Because with single variable derivatives, you don't get to just say, I'm going to treat this as a constant. Right? In some sense, with single variable derivatives, you have to actually deal with everything given to you in the function. With partial derivatives, you just get to write off and say, I'm going to treat all that as a constant. Totally awesome. Okay. All right, what does this look like? Now, we got to be. Was that a no? Okay, all right. Sorry, that's all right. We have to be careful with this. If you want to make geometric interpretations of calculus, and I gave you all this speech over the last few days here, so let me not repeat it. But if you're gonna do geometric interpretations of calculus, you need to know what geometry are you looking at. Are we talking about the calculus of graphs? Are we talking about the calculus of level sets? Are we talking about the calculus of something else? Right? The picture informs very importantly what the interpretation of the calculus is in that picture. Okay, so being very careful as such. Let's talk about graphs. Suppose I'm looking at a graph. You can see it right there, z equals, right? So I'm looking at a graph of a function, specifically now this function right here. Right, some function of x and y whose value I'm going to set equal to z. We're not going to worry about what the formula for f is. Okay, so being as that's a function and I'm looking at its graph, the graph, as we've previously discussed, is a surface, like so, right? And question, what does a partial derivative look like on this picture? Now again, I claim this is calculus of graphs because partial derivative is calculus. And I want to understand what it looks like on a graph. This is our first example of calculus of graphs. Okay, and the big idea is, if you're taking a partial derivative, there's two steps, and I already know how to interpret each step geometrically. So it's pretty straightforward here. Step one, I'm taking the partial with respect to y. That means x will be a constant for this discussion. So here's a constant value of x. That's a plane perpendicular to the x-axis. Said differently, that is a vertical plane. You might say in the y direction. Right? Constant value of x. And I know what happens to graphs. Right? If I have a graph like this and I take its cross-section in a vertical plane representing a constant value of x, well, then I get what's called a cross-section. It's just some curve then. Next, looking at that curve, this being the graph of my new single variable function, taking the derivative. Now, what happens when I take a derivative? And keep in mind, I'm taking the derivative with respect to y. That means I'm moving in the y direction. Of course, I'm moving in the y direction. That's the direction that remains after I've set x equal to a constant. Right? As I move in the y direction, taking a derivative, slope of the tangent line. So, nice simple punchline. If you want to take a partial, well, let me do it like this. Let me put a big box around this. If you want to take a partial derivative with respect to y, it's the slope of the tangent line to the graph in the y direction. Very often we'll just say it's the slope, right? But now do be careful, slope of the tangent line, of course, because that, in order to define slopes, we technically have to talk about tangent lines. Lines are what have slopes. Specifically also, and very important, and you might not say it every time, but you absolutely have to think it every time, it's the graph, specifically, whose cross-section I'm talking about. So there you go. And exercise for you all to do on your own. It's totally doable. Draw the analogous picture. Make the analogous argument for doing a partial with respect to x. And punchline is going to be that it's slope of the tangent line of the graph in the x direction. Y'all have a great weekend. See you later. Okay. All right. Let's see here. Quit? What's going on here?